Okay, so we are here, and let's actually go to the second derivative part, where we now understood that it is giving you better in terms of sharpening or the edge effect from this example. And let's actually see the most fundamental filter, okay, 2D filter I would say, is the Laplacian, okay. So you might have heard about the Laplacian operator, right? I mean, or seen this before, the del square f, right? Okay. So this essentially means that if it is a 2D, it will actually have the expression in the x direction and in the y direction. So second derivative in the x direction and second derivative in the y direction. We already derived it before, okay? And dou square f by dou x square, we already derived it, and I put the y factor also here because we have the y term also in the second expression, right? So dou square f by dou x square, you have only x component, y is remaining constant, y is not changing, and in the y part you have the x remaining constant, y is changing. And there is an important aspect. This is an isotropic kernel, okay? So that means it is independent of the direction of the edges. So it doesn't matter edge is in the horizontal direction or edge is in the y direction, because you are doing it in both direction equally, and you really don't have any direction sense here. So I'll just give a clue, just a minute. If I go back to the previous chart, okay, so here for example, okay, so there is a way actually we can get the directionality, okay, from the Laplacian itself, okay. So you can see over here, when there is a change from high to low, you have the highlight in the negative direction, okay. And then the problem for us is actually this region, I hope, right? Because here this is going from the basically a ramp to this, that also, but it comes in the opposite direction. And then from constant to this, again you have this particular peak, okay. So increase, you have this particular peak, but then again you have reduction, this particular peak is gone. So there's no significant way to say that the direction. But on the other hand, the first order differential may be, I'm just giving a hint, may be able to give the direction of the edges, or it is actually not isotropic, okay. It is sensitive to the direction of the edges. So we will have examples, so don't worry, okay. When we take the examples, it will become very clear to you, okay. So let's move on, okay. So the expression is nicely here, and now we need to implement it as a convolution operation. So don't forget the high level picture, right? Our operation is always in terms of convolution. So how shall I go about this? Okay, so how I put this kernel in convolutional terms, okay. So this is a complete picture. So del square f is, you have to add both dou square f by dou x square plus dou square f by dou y square, which is actually what happened over here, okay. So now let's see what happens, okay. So you see here, we just added up, you have a 4 f of xy component here. Now you put this thing into a matrix operation, okay. And what is that? Is this. Okay, so this is very, very interesting. Okay, let's spend some time understanding this. So x plus 1 y. Okay, maybe I'll start with this. So this is the center point. It has a weightage of 4. Okay, so that is what happening here. So minus 4 is coming and sitting at the xy location, which is actually the center point. Okay, let me just ignore that. Now, okay, all others. So all others in the sense like x plus 1, x minus 1, y plus 1, y minus 1. Okay, so basically nothing in. So this point is basically x minus 1, y minus 1. I don't have any value here. Okay, this is x minus 1. So this point is x minus 1, y minus 1. I don't have any value here, right? If you see over here, that is why it is 0. All other values like this guy, this guy, this guy, this guy is either x plus 1 or y plus 1 or x minus 1 or y minus 1. They all have values 1, right? Oh, wait, I think there's an error here. I mean, this is actually not, this is plus, okay. So there's a plus here, I will change that, sorry for that. So this values, whatever the kernel values that you are going to see is exactly this expression, okay. So the coefficient values are determined by the coefficients here, 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 and here, okay. So that those are actually going. I hope it is very clear. Okay, so this particular mapping to This one should be very clear by now. Okay. Okay, so very quick understanding. I just put this matrix so that it will be very easy. So this is your xy. Okay, so basically this is your y direction and this is your x direction. Don't forget that. Okay, so this is your origin sort of. So anything below in x and y direction is x minus 1, y minus 1, right? This coordinate, and this coordinate is in y direction. It is in x direction it is plus 1. And in y direction it is minus 1. So that is why this value. And this guy, this coordinate over here is plus 1 in both directions. So x plus 1, y plus 1. This point is advancement in y but behind in x, right? So that is why x minus 1, y plus 1. And you can see over here, okay, so these coordinates, wherever the coordinates are, you just see the value here and put that into this sort of a matrix. So minus 4 here because at f of xy, it is minus 4. That is why minus 4 here. And this is 0 because you don't have an x minus 1, y minus 1 in this expression. Okay. So that is the difference. Now a small update here because this can be represented in different ways. So here I am not having weight in the diagonal direction, the northeast, southeast and all these directions. I don't have any weight. I can create a new kernel which is something like this. Okay. And you added ones in all the places, and then of course you have to subtract by 8. Why this? This is important actually. You see over here the positive weights will be plus 4 and then you are subtracting by minus 4 so that your image is normalized. Similarly here the positive weight is 8, so you have to subtract by minus 8. Okay, and these two are related. Okay, the only change I just inverted. Okay, so minus 1 I just made it, then this becomes plus 4. Okay, so that is the difference. And similarly these two are related. Okay, so but all these are Laplacian kernels. Okay, so the original Laplacian kernel is this by strict derivation perspective, but you can have any of these kernels as your Laplacian. Okay, and one important striking factor which you can obviously see from here is the directivity, right? That is why this guy is important. Okay, so here this direction, this direction, this direction and this direction, it is all similar. Okay, so there is nothing majorly standing out. Similarly here it's all same in all directions. So this is purely isotropic, I would say, because it is same weightage in all directions. Okay, so that is why it is called isotropic kernel. So there is no directivity induced by the Laplacian sharpening. Okay, so that means after the edge enhancement or after the sharpening operation, after this filtering operation, edges irrespective of whether they are oriented in horizontal or vertical will get enhanced. Okay, so that is important to notice. So this is an example. Okay, so image sharpening using Laplacian. So this is an example. So original we have the moon image again. So if I do a Laplacian, I will get the edges. So you can see there is no particular orientation which is getting highlighted. It just enhances all the edges. So what is this operation I am doing? So this is the Laplacian. Okay, so that image is here. And now what I am doing is I am going to multiply this image by some value and add to the original image. Okay, so this is f of xy. This is the Laplacian, and then I am going to add them by a small factor. And if you see that, this entire operation will result in an image which is shown over here. And you can see the sharpness compared to this image. You just see the craters are all much sharpened compared to this. Okay, so this is original image. This is a sharpened image. Okay, so I did an image sharpening. Okay, so that's this is an interesting application because edge alone is really not very useful for me, but you should not stop there. As an image processing engineer, you should use that information. So what I did is, I first took the original image, took the Laplacian, I get something like this. I added this Laplacian to the original by a factor of c, and then I get this image. This is a very interesting operation and very useful operation. Okay, many times we do this. Okay, so let's move on. And this is also another interesting application. Okay, so these are all applications. So we started off the entire week with more understanding of the spatial operations. We had an explicit discussion on convolution and filtering. Spatial filtering is a very beautiful application of convolution. We started off with smoothing or averaging, different types of kernels associated with that. We saw some examples, for example, removing the shadowing effect from the image, that grain image, for example. Then we discussed about the median filter, which is again very useful. And now we are discussing about sharpening the image using differentiation, right? And one of the classical differentiation operation is the Laplacian. Okay, and that's what we are seeing. And now there is another interesting aspect. So now we are going to combine the smoothing and the Laplacian operation, come up with something which is known as unsharp masking or high boost filtering. They are related, and let's see what it is. Okay. So this is something which is actually what a literal meaning of it is subtract an unsharp or smooth version of an image from the original image. Remember the removal of the shadowing effect, the grain shadowing effect, similar to that. Okay. And this is heavily used in printing and publishing industry from 1930s. Still, people are following it. So the steps are something like this. Okay, you take the image, you blur the image. Blur is nothing but smoothing the image. Okay, so you average the image. Okay, you can use a Gaussian smooth, for example, or a box filtering, for example. You do that. Okay, then what we do is we subtract the blurred image from the original image. Okay, so when you subtract the blurred image from the original image, what you get is a mask image. Okay, something like a trend in the image or something like a very sharp edge in the image. Okay, so always remember that. So some details in the image are getting highlighted. Okay, and then you add it. Okay, then you add the mask image to the original image. So let's say, okay, let's put in terms of equations. So g of xy is equal to f of xy plus k into f mask of xy. So f mask is actually something which is some obtained using these steps. Okay, these two steps. So these two steps. Okay, so what is f mask? Is obtained from the original image. So original image, when you smooth it and subtract that smooth from this one, you get an f mask, and then you add it to the original image. You might think what sort of operation I am doing, but if you see the result, so let me just put the thing. So blurring is happening here. Okay, subtraction is happening here. Okay, and this is happening here, and see this k. Okay, if k is greater than 1, it is known as high boost filtering. If k is less than 1, it is known as unsharp masking. Okay, so let's see the result. And let me explain this using a graphical representation. Okay, so 1D again is easy to visualize. So you have an original image. Okay, so if I smooth it further, so your original image is smooth, blurred or smooth further, you get this sort of shape, right? A much more smooth. So the dotted line is original, and you see a smooth. So edges are gone, right? That's what the problem with the smoothing operation, right? Edges is getting much more smoother. So the sharpness in the edge is already gone. So you have a blurred signal, which is shown by the thick line. Okay, dotted line is nothing but the original signal itself. Now, if I subtract these two, what I get is these sort of differences. Whatever is difference here, that gets highlighted here. And now what I am doing is I am going to add this to this, and I end up getting over this one, this guy. Okay. Again, this operation is what actually doing over here. Okay. Okay, maybe let me just put it so that people understand. So this is what you have over here. Okay. And this entire thing is what you have over here. Okay. And then this thing is what you have over here. Okay. I hope I'm not really disturbing you. Okay. So this is, you may be thinking that, oh, this is very empirical, I have to, but people have come up with this after a lot of thought process. It is really not natural to think like this, but what we are essentially doing here is actually trying to find out, so here we didn't use Laplacian, remember that. So I want to correlate between these two concepts, okay. So here I'm using Laplacian to bring out the edges and then adding that edges by some factor to the original image, okay. So this is image sharpening using Laplacian, okay. But here, what we are doing is no Laplacian, but instead of that, I am smoothing the original image, subtracting to get the edges, and then you add it back to the original image. So this part, if you see this part, is similar, but then obtaining this part in the previous case was using Laplacian. In this case, this is using only smoothing. Okay, so that is the interesting part. So this is to show you holistic picture of how you can combine different operations. Now let's go to result. This is what you should be very much interested in. Okay, so you have the original image, again the same moon image. I smooth it, okay, I heavily blurred it, it looks pretty useless, but not really, because I subtract between these two, I get the unsharp mask image, okay, sorry, the mask image, and then what I do is I subtract these two and then add that back to original image. By a factor of 0.8 I get this, by a factor of 4.5 I get this particular thing, okay. So you see the difference? This is original image. This is really, really good. Almost similar to what we get by image sharpening using Laplacian, right? And look at this. Wow, this is really impressive, right? So don't worry, we will have all these in the hands-on exercises. So you'll be playing with all this. Even if you don't understand it, it's no problem at all. You should be able to do this. It's very, very quite straightforward, right? And that actually sort of explains all the concepts in a very nice way. So this picture actually, let me just put the equations over here. So what we are essentially doing over here is g of xy, which is the final image, okay, is nothing but f of xy, okay, plus k into some f mask of xy. Okay, so this k factor is what you're seeing over here, these two. Okay, so when k is 0.8, it is called unsharp masked, and k is 4.5, it is called high boost filtering. Okay, and this f mask is obtained, always remember that f mask is obtained by subtracting the f of xy, okay, from its smoothed f smooth, okay, of xy. And this guy is what you're seeing over here. Okay, so f of xy again is shown over here. Okay, so I hope everything is clear. It should be, okay, it's very, very interesting operation, and you should be able to come up with your own way of actually improving it. But this is heavily used in 1930s onwards. People are, if you talk to somebody that I'm doing unsharp masking, you don't need to explain all the hell of process. They will know that by, if they are already knowing the image processing, they will be knowing that. Okay. Okay, so that is on the aspects of second order filtering and related things. Now let's talk about first derivative. We didn't explore the first derivative because we declared that second order is good in sharpening. So we went ahead and discussed Laplacian and went about it. But first order is very interesting, and it has a very, very important application, which I will explicitly show you here. The gradient, right? So it is nothing but again dou f by dou x, first order only, but not only x is there, y is also there in this image, and you go for dou f by dou y, and not this point. It is not isotropic. It is directional. Okay, that's a very, very key factor. So hence, to make isotropic, we will consider magnitude. Okay, so we'll come to that. Okay, so ignore it if you don't understand it. Okay, so dou f by dou x, again it is nothing but in the x direction. Okay, so change, remember this, only one time or one shift, not like two shift in the case of a Laplacian. So x plus 1 minus x and y plus 1 minus y in both the directions. You come, and then if you want to express this, okay, so this expression, okay, so this guy is actually expressed in this way because you see x plus 1. So okay, this is, let me just, sorry for that. Okay, so this guy, right, this is actually y plus 1, right, this is in the y direction. So you see this, and there is a problem here because it's 2 by 2. Okay, so this is your center pixel, that is considered as your center pixel, that is 1 minus 1. So this guy is xy. Okay, sorry, let me just erase it. Okay, so what I'm saying actually is okay, so this is your xy for this guy. Okay, and then this naturally will become your x comma y plus 1. Okay, so that is why this guy is 1 and that is put over here, and this guy is minus and that is put over here. Both others are 0. Okay, and similarly I can come up with minus 1 minus 1, which is nothing but this guy. Okay, so that is the operation. And we call it as gx and gy if you want actually. And then what we see generally is we do individually. So you do convolution with this kernel and this kernel and then take the magnitude. Okay, so then you may ask me the question, what about the phase? Because I can have the phase of this image. So phase of xy, at each pixel is nothing but tan inverse of gy by gx, right? So this can be extremely useful. So we'll come to that. Okay, so let's actually do some more operations. So now you just talked about is basically in the horizontal and the vertical direction. That's what you see over here. But you can have over in the diagonal direction also. Okay. So this is in this direction and this is in this direction. Okay, so this was discovered by a famous image processing engineer named Roberts, and hence the name Roberts gradient operators. Okay, and as we discussed here, this is only 2 by 2. Okay, but that's not very nice because then it's really not symmetric. Okay, so or I would say it's really there's a problem of the centering, right, as we experienced over here. So in this case, where shall be the center? It's very difficult. So it's always important that you take odd filter, odd kernel filter, 3 by 3 for example, because you have an exact center. There's no confusion about it. And in the case of first derivative, some of the Sobel filters or Sobel kernels, okay, again another person named Sobel, are something like this. This you already saw it in the previous lecture as well as in the quiz, I think. Right, in the quiz you might have seen this. So this you can see over here is actually having a filtering in this direction. Okay, so I don't know, I mean maybe I'm getting messed up in having the directions correct, because this is actually in this direction, right, because your subtraction is in this direction and this is actually in this direction. So this should be gx, right, and this should be gy. So I'll correct that when I upload the slide. I will correct that, sorry for that. So because this is in x direction, I mean, basically, the gradient is happening in the y direction, right? Because 1 minus 1, 2 minus 2. So this is in the y direction, and this is in the x direction, right? And so this should be gx, and this should be gy. Okay. But anyway, it doesn't matter. The kernels are formed to have explicit y and x directions, and then as usual, you take the square root of that or the magnitude of that. You get the image. Okay, and one important thing I would like to stress here is the value of 2 can give you indirectly, even though that is needed because you have minus 1. So to balance it out, okay, let's put that minus 1, this get cancelled out, right? Minus 1 and 1 gets cancelled, minus 1 and 1 gets cancelled. So you can put any value, literally any value here. It can be just minus 1 here. It doesn't matter, but 2 will give some importance to this particular center value. So it gives sort of a high weightage to the pixels. Okay, sorry. So that means some smoothing. I mean, if you literally want to see that, there's some smoothing happening, but you ignore it. If you're really not particular about it, you can ignore it. But there is some smoothing effect which is happening because of that 2, the value 2, because there is some weightage. Okay, so some weightage is given to the center axis, this axis and this axis. Okay, so that's interesting to see. Okay, so let's actually see this in some operation, in some application, so that you get better picture of what I'm saying. Okay, so this is a lens image actually. Okay, so the image of a lens. So this is the original image. So if I consider only gradient of x, which is nothing but dou f by dou x. Okay, so then the problem is actually we are getting edges, these edges. Okay, so if you see here, these edges are highlighted. This is gone actually, right? This part is gone. But on the other hand, if you see here, this part is highlighted. This part is also highlighted, but in this direction, it is gone. So that means the edge enhancement is happening in this direction, and this, in this case, it is in this direction. Again, that label mismatch is there. I think I'm consistent in making that error. So please ignore that. You be consistent in ignoring that error. Okay. But when I upload the slide, I will make this correction. So don't worry. Okay. But the highlight point I would like to stress here is, okay, there is heavy directivity. This is not isotropic edge detection. Okay. So if I individually consider the X and Y filters, I could see that in one case I am having the this direction, which is nothing but the Y direction edges, and in this case the X direction edges are highlighted. If I take the magnitude, I have the nice curve coming together, right? It's a full circle coming together. That means the square root of this guy plus square root of this guy, I mean square of these guys, basically the absolute of gradient in x and y directions, you get the full direction. Then it becomes isotropic. So that's what I was telling. Okay. So gradient, first order gradient, okay, first derivative is actually inherently directional. It is not isotropic. It is anisotropic. To make it isotropic, you need to take both directions and then do what? Take the magnitude of that. Okay. So, but if I take the direction, okay, so if I take the direction, you may get something like the direction of the edges. So, which way the intensity is changing, that part you could be able to actually utilize. So, we will have a very beautiful application of that at some point of time. So, we will not discuss that. So, if I take the angle, so here I am talking about the magnitude, right? If I take the angle also, because I have x and y component, I can take tan inverse of y by x, I will get the angle. I can use that for directional finding, okay? And that is actually edge direction I am saying, which direction the edge is. So I can find that, okay? So for example, this circle, how the direction of these edges is going, I can find that out and I can use it for some practical purpose. So we will discuss in detail when we go and discuss that topic, okay? So that sort of completes the first order derivative or first derivative operations also. Okay, so I think that sort of concludes the basic filters, okay, the basic spatial filters. Okay, so just to reiterate, we talked about smoothing. So we talked about the box filters, the weighted average filters, the Gaussian filters, right, in detail. Then we talked about a nonlinear filter named median filter. Then we talked about sharpening. And for sharpening, we started off with Laplacian because obviously Laplacian has the advantage of isotropic and it gives you like clear edges. So we use that for something like sharpening of the image. Then we talked about the unsharp masking and the high boost filtering, for example, where I don't need to actually do any gradient operation, but I can actually subtract the smooth image from an original image to create a edge image and use it for something like unsharp masking and high boost filtering. And last but not the least, we do have first derivatives also. And we discussed about different kernels, right? Different types of kernels. 2 by 2 kernels, starting off with the conventional ones, then the Roberts, then the Sobel gradient operator. Okay. So all these, and the importance for first derivative is like it gives you directionality, and that can be advantageous in some cases to find out the direction of the edge. Okay. But if you take the magnitude of the, both directions, then you end up in getting similar result as that of the Laplacian. But obviously, the importance of Laplacian is it highlights the edges much higher. Okay, so with that note, we will finish off the lecture series on the basic spatial filters and spatial operations. Okay, so in the next few lectures, I will highlight some of the advanced operations, okay, which will be extremely useful for you. Okay, so till then, bye for now.